All right, this is the quiz for chapter 5. A shopper in a supermarket pushes a cart with a force of 40 newtons directly at an angle of 60 degrees downward from the horizontal. Find the work done by the chopper to move down a 25-meter length of aisle. All right, so here's my cart. I'm applying a force that is 40 newtons at an angle of 60 degrees, and my displacement is in this direction, and my displacement is 25 meters. All right, so my work is just FD cosine theta. That's going to be 40 newtons times 25 meters times the cosine of 60. That's 40 times 25 is 1,000. Cosine of 60 is 0.5, so it's 500 joules. So the answer is B. Outfielder throws a 0.2 kilogram baseball with a velocity of 35 meters per second. Follows a projectile path. The angle is 30 degrees. I want to know what is the kinetic energy at the top. Now I know that the velocity in the y direction at the top is 0, and the velocity in the x direction is going to be v naught cosine theta. All right, so I need to find out what is this velocity. So the velocity in the x direction is 35 meters per second, cosine of 30. And that's equal to 30 meters per second. So that's my velocity at the top of the trajectory when the velocity in the y direction goes to 0. And so the kinetic energy is 1/2 mv squared. The mass is a 0.2 kilogram. It's 0.1 times 900. It's going to be 92. I must have kept more sig figs along the way. So 92 joules. Or I come up with 90 here, but the way I came up with 92 is, let me just show you. I put in my calculator a little bit differently. I squared this number, so I kept more decimal places for this number, and that's equal to 92. All right, figure shows a cheerleader thrown in the air. She reaches a maximum height of 6 meters. What is her initial speed? We did a problem very similar to this. I know that my potential energy down here is equal to 0. My kinetic energy equals 1/2 mv squared. At the top, the kinetic energy equals 0, and the potential energy equals mgh. I know that the sums of these two have to be equal, so I say mgh equals 1/2 mv squared. My masses cancel, and I solve for v. That's the square root of 2. It's going to be 11 meters per second. That's A. I have a block of 1 kilogram attached to a spring with a spring constant, 1200. So K is equal to 1200. Spring is compressed by 20 centimeters. That's going to be X. And I'm going to convert that into meters. That's 0.2 meters. I want to know what is the velocity at X equals 0. So I want to know the velocity at the equilibrium position. I know at this position that the kinetic energy equals 0 because it's not moving, and the potential energy equals 1/2 kx squared. Over here, I know that the potential energy equals 0. That's because x equals 0, and my kinetic energy is 1/2 mv squared. Just like before, I know that the sums of the energies have to be constant, so I say that 1/2 kx squared equals 1/2 mv squared. I can get rid of the 1/2s, they cancel out. I'm looking for the velocity That's going to be the square root of 1200 times x squared, that's 0.2 meters squared. Being very careful to convert this into meters. Divided by my mass, which is 1 kilogram. We get 6.9 meters per second. That's going to be B. Is it possible to do work on an object that remains at rest? Well, work equals force times displacement. If it remains at rest, that means the displacement is 0, so the answer is no. Box is being pulled across a rough floor at a constant speed. What can you say about the work done by friction? Well, I'm pulling it. My velocity is in this direction. My kinetic friction is in that direction. So work done by the kinetic friction is Fk d times the cosine of the theta between the two. So since my velocity is in that direction, my displacement's in that direction. That means that theta equals 180, and cosine of 180 is -1. So this is negative Fkd. So that means it does negative work, B. Can friction ever do positive work? The answer here is yes. I'm not sure if I gave y'all this. There's one scenario where I can have friction do positive work. Say that I have a box on the back of a truck. The truck is moving with a velocity in that direction. That means that the frictional force is acting in this direction. Now, the box wants to move off the back of the truck, and in order for it to stay on the back of the truck, the force due to friction pulls it, so to speak, and it remains on the back of the truck. So in this case, Fk is in this direction, and my motion is also in this direction. So that's positive work. So the answer is A, yes. In a baseball game, the catcher stops a 90-mile-an-hour pitch. What can you say about the work done by the catcher on the ball? Here's the catcher. He catches a ball, and in the course of catching that ball, he imparts a force in this direction. However, the displacement of the ball is in that direction. Since the force and displacement are in opposite directions, that theta equals 180 degrees, and cosine of 180 equals -1. So the catcher has done negative work. Well, we can also think about this in terms of energy. It's like the catcher is taking away energy from the ball, and in order to take away energy, that means that you're doing negative work. A ball tied to a string is being whirled around in a circle. What can you say about the work being done by tension? We're going to get to this in a later chapter, in a couple of chapters. If I have the tension, if I have this object moving in this direction, my tension is in this direction, towards the center of the circle, but my displacement is in that direction. So the angle between them is 90 degrees, and the cosine of 90 equals 0. So my work then, which is Fd cosine theta, is also equal to 0. So the tension does 0 work at all, no work at all. That's option A. You lift a book with your hand and move in such a way it moves up at constant speed. While it is moving, what is the total work done on the book? Well, the key here is that it's moving at a constant speed. And if it's moving at a constant speed, that means that the acceleration equals 0. That means that the net force equals 0, or the sum of all the forces. And if that's the case, then the work equals 0, at least the total work equals 0. Now I can think about the forces individually. Now the force due to the hand is doing Fh times my displacement. And the force due to gravity is doing mg times my displacement. But since those forces are equal but opposite, they're going to cancel one another out. So one of them is going to be Fh times d is going to equal to the negative of mg times d. So when you add them together, they'll cancel out. By what factor does the kinetic energy of a car change when its speed is tripled? Well, kinetic energy is that. If I triple the speed, that means I get a factor of 9 over here, so that's D. Car 1 has twice the mass of car 2, but they have the same kinetic energy. How do their speeds compare? Well, I know that my kinetic energies are the same. This is my expression for kinetic energy. Car 1 has twice the mass of car 2. So we'll say car 2 has mass m. That means that car 1 has mass 2m. All right? So if car 1 has mass v, that means that car 2 has to have mass root 2v. Because you see here, I square this root 2, and it will give me a factor of 2, which will match the left-hand side of the equation. So that is going to be option B. Two stones, one twice the mass of the other, dropped from a cliff just before hitting the ground. What is kinetic energy of the heavy stone compared to the light one? Well, I know they accelerate at the same rate for both of these, regardless of the mass. So they're going to have the same velocity. The velocity of the first stone will equal the velocity of the second stone, irregardless of the mass, and that actually comes up in the next question. However, they have different kinetic energies because the kinetic energy is proportional to the mass. So the one with the bigger mass will have the bigger kinetic energy. And so it's going to be a linear relationship. So if I have twice the mass, I have twice the kinetic energy. So the heavier stone has twice as much. That's option D. Child on a skateboard is moving at a speed of 2 meters per second. After a force acts on the child, her speed is 3 meters per second. What can you say about the work done by the external force on the child? Well, the force has increased her speed, which has increased her kinetic energy. That means that she has done positive work. It has increased the kinetic energy, which means positive work has been done. You can also think about it. Here's my person on my skateboard. My force has to be in this direction, which is also in the direction of her motion. I say that it has to be in that direction because it's causing her to speed up. Car starts from rest and accelerates 30 miles an hour. Later it gets on a highway and accelerates 60 miles per hour. Which takes more energy, 0 to 30 or 30 to 60? Think about how my kinetic energy is plotted against velocity. Remember, kinetic energy equals 1/2 mv squared. So this relationship is a quadratic relationship, which is a parabola. So as I get to higher and higher velocities, my kinetic energy takes more and more energy. So let's say that I go from 0 to 30. Say the blue mark there is 30. I require this much energy to get up to 30 miles an hour. However, to get up to 60 miles an hour, I require a lot more energy. So as you speed up, your car just requires more energy to keep going faster and faster. So the higher speeds get increasingly more difficult to maintain. Now this is apart from wind resistance. Now it is also true, which many of you might know just from experience, that the faster you go, the more wind resistance you feel. That's true, especially if you ride a bike, that once you get over about 15, 20 miles an hour, the wind resistance just becomes a lot bigger. So this is irregardless of wind resistance. That's a separate factor. This is purely just the energy required to move. Is it possible for kinetic energy to be negative? Well, no. All right, kinetic energy is a scalar quantity. And also, if you look at it mathematically, I remember work was also a scalar quantity, but it could be negative. Remember we said that that negative didn't mean that it was a direction, but instead it meant that it was taking away energy. That's not so for kinetic energy. There's no mathematical way for it to be negative, because notice how the velocity is squared. In fact, this is the speed, but even if it was a velocity that included the either positive or negative direction, when you square it, you lose that information. All right, so the answer is just no. You and your friend both solve a problem involving a skier going down a slope, starting from rest. The two have chosen different levels for y equals 0. Which of the following quantities will your friend agree on? I'm going to skip this one, actually. Let's just skip it. It's not terribly important. All right, two paths lead to the top of a big hill. One is steep and direct, while the other is twice as long but less steep. How much more potential energy would you gain if you take the long path? This goes back to the fact that potential energy, or gravitational force, the force weight, is a conservative force. right? That means that it conserves energy. What that means is if I go up a mountain, I can take two paths. I can go straight up, and if I go straight up the path, I cover a height, h. Or I can take a more circuitous route. However, I'm still covering a height, h. It doesn't matter which path I take, I'm still gaining the same amount of potential energy. Right? So the answer here is A, the same. I'm still gaining the same amount of potential energy. Now, I'm requiring more energy to go up the circuitous path because I have a non-conservative force that's acting on me, the force of friction. And that acts over a long distance, taking the green path here, because frictional forces are non-conservative and they don't conserve energy. The answer here is A, the same. How does the work required to stretch a spring 2 centimeters compare with the work required to stretch it 1 centimeter? Remember, potential energy of a spring is 1/2 kx squared. So if I stretch it twice as far, which is what I'm doing here, I get 4 times the potential energy or 4 times the work required. Mass attached to a vertical spring causes the spring to stretch. Let's just draw a picture here. As that mass goes down, x of the spring increases. But as it goes down, the height of the spring decreases. So since x increases, the elastic potential energy of the spring goes up. But the gravitational potential energy goes down. So that is PES increases. That's option D. 3 balls of equal mass start from rest and roll down different ramps, all of the same height. Which ball has the greater speed at the bottom of its ramp? Now, many of you put this answer, but that is not correct. In fact, correct answer is I'm starting all at the same height. So they have a certain amount of potential energy. They're all going to the same level at the bottom. And so all that potential energy is converted into kinetic energy. They're all going from the same height, so they're all going to have the same kinetic energy at the end. That means that they all have the same speed. So D is the correct answer. By the way, what if we had frictional forces at work here? Which one would be going faster? If there were frictional forces applied, ball A would be going fastest because it would have a shorter distance over which the friction would act. So it would take away less energy. Truck at excavate rest rolls down a frictionless hill and attains a speed of 20 meters per second at the bottom. To achieve a speed of 40 meters per second at the bottom, how much times higher must the hill be? So I want my velocity to be twice as big. I know that at the top, my potential energy is maximum, my kinetic energy is 0. And this is going to equal my kinetic energy at the bottom and no potential energy at the bottom. Potential energy up here, only kinetic energy up here. mgh equals 1/2 mv squared. I want my speed to be twice as big. That means that I get a factor of 4 over here. So I have to start out 4 times the height in order to get a bigger speed like that. The box is sliding on a frictionless flat surface that runs into a fixed spring, compresses the distance x to stop the box. If the initial speed of the box were doubled, how much would the spring compress in this case? All right, so I have only kinetic energy here. And then I have only potential energy here. That kinetic energy, 1/2 mv squared, is going to equal my potential energy, 1/2 kx squared. It's all going to be transferred in. If I double my speed right here, that's going to double my compression, x. So the answer is D, twice as much. Notice that your speed is squared, but so is your displacement x. All right, following Kathleen, start from rest. On frictionless water slides with different shapes, at the bottom, whose velocity is greater? Well, it doesn't matter about the shapes because they're frictionless. So even if Paul goes down a slide like this, and then Kathleen goes down a slide that's a lot bumpier like this, it doesn't matter because they're frictionless. They're going to have the same change in height, and so at the bottom, their velocity is going to be the same. Now, if there was friction, the person with the shortest path over which the friction would act, then the friction would do less work, and so that person would be going faster. So say, for example, let's say that there was, the answer for this one is C, that they're both the same, but let's say that we do have kinetic friction, and we have a slide that goes like this, and then we also have a slide that goes like this, a much longer slide. The person at the end of this slide would have a little velocity. The person at the end of this slide would have a lot of velocity. That's because the work done by friction here is a lot bigger. So the work done by kinetic friction is a lot bigger because the displacement over which that frictional force acts is bigger. Mike applies 10 newtons of force over 3 meters in 10 seconds, and Joe applies the same force over the same distance in 1 minute. Who did more work? Well, they give the time here, but work is independent of time. So they both do the same force, same distance, both did the same amount of work. So that's C. Mike performed 5 joules of work in 10 seconds, and Joe did 3 joules of work in 5 seconds. Who produced the greatest power? Now this is different. I have 5 joules in 10 seconds. Remember, power equals work over time. So that's 0.5 watts. And then I have 3 joules over 5 seconds. Less work, but less time gives me 0.6 watts. So that was Joe then produces more power, or B. Engine number 1 produced twice the power of engine number 2. And we conclude that engine 1 does twice the work as engine 2. No, you cannot, because you don't know the time. Remember, power is this relationship between work and time. Just because something produces twice the power doesn't mean necessarily it produces twice the work, because it could be that you have a relationship like this, that it produces twice the power in half the time. This is about the same amount of work. So the answer is B, no. When you pay the company for a kilowatt hour, what are you actually paying for? Well, let's just think about this. I have a kilowatt times hours, or I can think of, I'll just say watts times seconds. That's power times time. Watts is joules per second times second. The seconds cancel out. So I'm paying for joules, which is A, energy. Entergy, the company Entergy, doesn't care what power you use. They only care what energy you use. Like you could use all of your power on day 1 of your billing cycle and you'd still pay the same as if you used all of your energy over the entire thing. So when we use the word power, often what we mean is energy. Just a couple more. Which contributes more to your cost or electric bill? A 1500 watt hairdryer or 600 watt microwave oven? Okay, well, even though the hairdryer does have a higher power rating, it depends on how long each one is on. So if you use your hairdryer as much as you use your microwave, which may or may not be the case, I mean, I tend not to use my hairdryer as much as I use my microwave. But you can use more energy with your microwave if you use it for a longer time.